Hello everyone, myself Pratham Tyagi and this is my teammate Rajiv Dabas. We are here to present our minor project presentation on CFD based analysis of a motor blower system. This project is guided by Dr. Sachin Gupta. So what exactly is a blower? A blower is a mechanical device that increases the velocity and pressure of air or gas and directs it to a specific location. In simple terms, it's a fan but more powerful, and it just doesn't move air, it pressurizes it. So what is the working principle, you may ask? So it uses an impeller rotating a pair of blades inside a casing. The impeller draws in air and increases its velocity, then converts that velocity into pressure. Uh, 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 for the pressure range question, blower system usually works between the pressure range of 1.1 to 1.2 bar, slightly above the atmospheric range. There are different type of blower systems as centrifugal blower, axial blower, and positive displacement blower. Next up, we have the need for the CFD analysis blower system, a general question. So the main need for this analysis is to predict performance virtually, which supports reduction in cost and time. It helps us visualize flow behavior, identify problem areas such as recirculation zones, flow separation zones, and energy losses zones to optimize design changes and to ensure reliability, and eventually supports innovation to test design changes quickly without any physical constraint, any physical prototyping. Next up, we have different type of objective for this analysis that are defined, which is number one, evaluating pressure drop within the blower system, analyzing airflow patterns to assess the temperature rise, to determine efficiency, and to support potential design optimization. So these are some of the objectives that we specified for this analysis. Next up, we have a comparison of why did we used SolidWorks flow simulation module rather than ANSYS Fluent. So my teammate will shed some light over the decision.
Now, as to why we are using the SolidWorks flow simulation tool over ANSYS or other simulation packages is due to the following reasons. The first one is the seamless CAD integration it provides due to being built into the SolidWorks platform. The next one is reliable material property handling. It is also due to the vast libraries that SolidWorks platform provides. And the next one is no data loss in workflow. This is an extension of the first reason, as the tools are as the CAD and simulation tools are integrated. There is no data loss between the transition from CAD to simulation. And lastly, this tool is very optimized for design engineers. Now let's look at some of the equations that we are using for our flow analysis. First, there are the governing equations that are the basis for the CFD analysis. These are the continuity equation, momentum equation, and energy equation. Similarly, there are the blower performance parameters upon which the performance of any blower system will be rated. These include the flow rate, the pressure rise, and work per unit mass. And lastly, there is efficiency and losses in the blower system. These include the total to total efficiency, the static efficiency, temperature rise, and system pressure drop. The CFD solver automatically handles the complex governing equation, and our role is to simply provide correct inputs, boundary condition, and then interpret the results that the solver provides. When we are doing a CFD analysis, we have to provide a mesh for the solver to apply equations to. And now we might ask, what is meshing? It is simply the process of dividing the blower geometry into small elements where the solver can easily apply the equations required. There are various types of mesh that we can use here, like the structured, unstructured, and hybrid mesh. Also, there are some quality parameters for meshes that are aspect ratio, the skewness, and refinement parameters for the meshes. When we select one type of a mesh, then they usually come with a trade-off. And these are that the finer mesh that provides higher accuracy takes much more computation time than a coarser mesh, which is faster than the finer mesh, but it also loses a lot of the details. Now, there are various approaches that may be used for performance analysis or any of the analysis that we are doing here, such as the analytical approach, experimental approach, or the numerical CFD approach. We are going with the CFD approach the as it befits the growing theme in the design industry of reducing the design timeline and also due to the higher accuracy that it provides. In analytical approach, the conclusions that we reach upon are quite quick and simple, but they are not accurate enough for any design optimizations. And in the experimental approach, the the results that we get are very accurate, and there is a lot of real world validation due to them being physical tests. But it is also very costly, time consuming, and requires a lot of specialized testing equipment that will be used in the experiments. Now, these are the results that my teammate will shed some light on.
So for the result part, we have received these results after some iterations in the SolidWorks flow simulation, 225 iterations to be specific. These iterations are performed on the basis of convergence of the result. For the velocity contours part, we received the velocity flow rate as 100 meter per second, in which minor low velocity zones near the volute tongue suggest small recirculation regions. For the temperature contours part, we retrieved some slight rise from 293 Kelvin to 300 Kelvin, confirming low thermal losses and efficient aerodynamic performance. For the significance, these results are converged, which validate stable flow behavior, good pressure recovery, and uniform outlet condition for the blower. Next up, we have a result contours for the velocity and flow trajectory after 229 iterations. These iterations are performed by the SolidWorks flow simulation to refine the result based upon our geometry and our requirement. So the significance of these both different result and in the different iteration timeline, we received these results as a steady and converged result, confirming effective aerodynamic performance and consistent flow behavior within the blower. Next up, we have are potential optimization possibilities that arise after this analysis for our blower system. First one is the impeller design of potential optimization. We can definitely modify blade angle, curvature, and the thickness of a blower system for the better pressure rise and efficiency. We can definitely change casing and volute shape, and we can make it more uniform to have more efficiency in our workflow. For the inlet and outlet geometry, we can definitely smoothen entry and exit ducts to minimize pressure drop. We can do mesh refinements. We can do different mesh refinements by defining mesh controls in our geometry in the CFD, which can help us uh, give better results in the critical zones, which are need to be captured very critically for the flow behavior. We can have a different selection of material from the materials library of SolidWorks, due to which we can enhance our thermal management area, and we can definitely have a better operating parameters for our blower analysis to optimize blowers speed and flow rate with operating conditions for maximizing performance. So these are the research references and CAD representation module that we used for referring our study for doing the performance analysis of our motor blower system. Thank you so much for listening to our presentation.